Hi class, this is Mr. Morris, and today we're talking about enthalpy of reaction and potential energy diagrams. So we're going to start out on this first page just kind of talking about enthalpy. We defined it very briefly in a prior set of notes. Enthalpy is the amount of energy content in the system. So the amount of heat or energy content of the system, that's our general definition. It's energy content or heat content. Enthalpy of reaction, which is represented by delta H Rxn, is the change of enthalpy when a reaction takes place. So we have a way of measuring that. We've got a lot of different ways of measuring these types of things. But we also want to know how to calculate it. And we're going to be calculating that from enthalpies of formation. That's really what we're going to focus on in pre-AP. In AP, you go a little deeper into several different methods of calculating this. Enthalpy of formation is the heat that is absorbed or released when 1 mole of a compound is formed from its elements in their standard states. So that is kind of specific. We're not going to trick you with this year by any means, but standard states are going to be at the temperature of 25 degrees Celsius. So what that means is like oxygen, for instance, at room temperature is a gas. So O2 gas is in its standard state, where O2 liquid would be very, very cold. That's what we're talking about there. Standard state is defined as at 25 degrees Celsius and a pressure of 1 atmosphere. Alright, so the enthalpy of formation of elements in standard states is 0. So that's a really important thing to keep in mind. For elements in their standard states, it's going to be 0. We're going to use this, so don't let this get past you. I'll refer back to it when we start doing problems. That's a really useful fact. When you see an element, if it's in its standard state, the value of enthalpy of formation is going to be 0. And then we've got our general formula here. Delta H of reaction equals, and that sigma, that capital sigma sign means summation. So the summation of the products minus the summation of the enthalpy of formation for reactants. So it's the difference between the sum of all of the enthalpies of formation of the products minus reactants. Again, this term means the sum of enthalpy of formation values of all of the products. And yes, the coefficients matter. We have to multiply by coefficients. That's the big number out front of your compound. And then enthalpy of formation of reactants, that's going to be the sum of the enthalpy of formation values for all of the reactants. And yes, our coefficients do matter. So this here is just a huge table. Something like this would be made available for a question like this on a test, on the final exam, or on any formatives that we give you between now and then, where you would be expected to do these calculations. We maybe wouldn't give you the whole table. We'd probably just give you a few values, the ones that you actually need. Let's do our first example. This is an example where you are using the enthalpies of formation to calculate the standard change in enthalpy for the thermite reaction. Thermite reaction is the reaction that's shown below. We want to know what is the enthalpy of formation. Not enthalpy of formation, the enthalpy of the reaction. So that's what I'm looking for, is delta H of the reaction. Remember that delta H of the reaction is going to equal the sum of enthalpy of formation for products minus the sum of enthalpy of formation for the reactants. This is where it becomes very important to make sure we know the difference between products and reactants, of course. Products are on the right side, right there, and the reactants would be on the left side. Don't forget to pay attention to coefficients. All right, so I've got what I'm going to be doing here to find the delta H of the reaction is taking the enthalpy of aluminum hydroxide or aluminum oxide, sorry, Al2O3, plus the enthalpy of iron, but I've got to multiply that by 2. 2 times the enthalpy of formation of iron minus the enthalpy of my reactants, which is going to be 2 times the enthalpy of formation of aluminum minus or plus the enthalpy of formation of Fe2O3. Couple things for you to notice when you're looking at problems like this. A lot of times it's a lot more simple than it looks. I see aluminum as a solid. Well, that's a single element by itself. An element in its standard state is 0, remember? So aluminum and iron, their enthalpies are just 0. That's going to make our math a lot easier. Now we want to look up Fe2O3 as a solid and Al2O3 as a solid. So looking up here, Al2O3 is right here with negative 1675.7. And then Fe2O3 as a solid is right here. Fe2O3 as a solid is negative 824.2. Okay, so looking at that information that we just got, I could calculate it. Delta H of the reaction equals, well, the enthalpy of formation of aluminum oxide is going to be negative 1675.7 plus 2 times the enthalpy of formation for iron. Oh wait, that's just 0, so plus 0, which that's really not going to do anything. I could actually leave that out. Minus the enthalpy of formation of, well, 2 times the enthalpy of formation of aluminum. Aluminum is just 0. I could leave that out. So I really don't need these two factors. And the enthalpy of formation of Fe2O3, which is negative 824.2. Then you can just plug that into your calculator or do your mental math, either way, and get your answer. And I get negative 851.5 kilojoules for every mole of reaction that takes place. Okay, that's the general idea of how to do this. Let's move on to one more example, and this is going the opposite direction, because sometimes all the values are not found in a thermodynamic table. For most substances, it's not actually possible to go into the lab and directly synthesize a compound from its free elements. So the heat of formation of substances has to be found by working backward from its heat of combustion. So we've got an example down here. It says to find delta H of formation of C6H12O6 from the following information. And it gives us the heat of formation of carbon dioxide and water. It also gives us this value. This is the heat of reaction. So remember, it's heat of reaction, or enthalpy of reaction, is products minus reactants. And yeah, I know it should have the summation sign and all that, but just to give you a general idea, the enthalpy of products minus the enthalpy of reactants. All right, that's our equation. Well, in this case, I already know delta H of reaction, so I'm going to plug that in. Negative 2,800 kilojoules equals, and then our products are 6 carbon dioxide and 6 water minus, and it's going to be just C6H12O6 and 6O2. I hope you realize that O2 as a gas is just the standard state of diatomic oxygen. So I'm actually going to get rid of that factor. So we can just start plugging numbers in. We've got negative 2,800 equals, and then I have 6 times the enthalpy of formation for carbon dioxide, which is negative 393.5, plus 6 times for water, negative 285.8, and then minus the HF that I'm looking for, HF of C6H12O6. So now I can just put these numbers in a calculator and figure out what it is. If I wanted to solve for HF, I could just add HF to the other side. I end up with HF minus 2,800 equals 6 times, and actually I'm just going to do that in my calculator right now and get the answer for what 6 times negative 393.5 plus 6 times negative 285.8 is. And I get negative, whoops, I've got my eraser out, sorry, I get negative 4,075.8. So if I actually wanted to figure out what heat of formation is, I got to add 2,800 to both sides. Enthalpy of formation equals, becomes positive because I switch sides, 2,800 minus 4,075.8, and I get negative 1,275.8 kilojoules per mole as my heat of formation for this compound C6H12O6.